Okay, in the last video we looked at the squeeze theorem, and I want to apply the squeeze theorem to find two, well, at least one, and then we'll find the other one from this, well, we're going to find this one right here. The limit as x approaches 0 of sine x over x is equal to 1. This is a limit we're going to prove. We actually, when you go back, if you went back to when we did things numerically, we looked at this numerically. And we saw that the limit appeared to be approaching 1, and it in fact is equal to 1. Problem is, if I plug in directly 0, like, can we do that? I get sine of 0, which is 0 over 0. I get that indeterminate form. So that's not analytically how I can do it. We're going to use this limit to evaluate this limit, which also is indeterminate form 0 over 0, but this limit turns out to be equal to 0. And these two limits together are very useful, and we will need them later on in the course. So we want to spend time proving this one. And this one's going to be different because we're going to use the squeeze theorem, but in order to set that up, we have to do some geometric constructions. And so this illustrates the fact that we've looked at limits of functions algebraically or analytically, and I gave you three sort of techniques. Well, sometimes those techniques don't work, and so we have to do other things. And so finding limits of functions are not always as cut and dry, so to speak, as that. What I'm going to do is I'm going to draw the arc from a unit circle, just this quarter circle here. The radius is 1, you can see that. I just need the first quadrant here. And then I've got a line at an angle, central angle of theta here, okay? And the line is going to come out this way. And I'm going to draw some triangles here in a minute. And I've got some formulas and area formulas for you to remember, or you might not know about circular sectors and the area of those. So we're going to use those to proceed. I'm going to start with the naming some points here so we can talk about the different triangles. This I'm going to call point O, kind of for the origin. And then where it intersects with this unit circle, this quarter circle, I'm going to call that point P. And then out here where, from this point down here, let's call this point A. From this point A, which is obviously the point 1, 0, if we're thinking about this is the x-axis and this is the y-axis, I'm going to go vertically up at a right angle to connect with this line up here. Let me just draw a dashed line for that. Okay, so this is going to be 90 degrees here, 90 degrees here. And this point right here where this vertical line intersects this line I've got coming out at angle theta, I'm going to call that point T. Okay. Now, I want to form a couple other triangles here. I want to look at dropping a perpendicular from this point P down, so this is 90 degrees again, okay, to this point. And I also want to draw a line from P to A, dashed line, just to help with visualizing things. Okay, so what I want to take a look at is the couple of triangles here I formed. I want to look at the area of those triangles. I want to look at the area of triangle OAP. Remember how to do geometry triangles? OAP. Those are the vertices of my triangle. Does everyone see the triangle I'm talking about? There are several triangles I can pick out, but this is the one I want. Right? So what is the area of any triangle? It's 1/2 the base times the height. All right, 1/2 the base times the height. So the area of this triangle is 1/2. What's the base? What's the base of this? What's the distance from O to A? It's obviously 1, right? So the base is 1. And what's the height now? That's where we need to use a little trigonometry. Well, the height is equal to the height or altitude is this perpendicular distance right to the top. So it's not this length, right, or this length, but it's this length. That will be the height of our triangle. What's this length? Well, this dashed line helps me to construct another triangle. This is not triangle OAP, but this is a right triangle, right, because of this right angle here. Right? This is a right triangle. And we know something about right triangles with trigonometry. And this side length opposite the right angle is the hypotenuse. Right? This side length is sometimes called the adjacent side if we're talking about angle theta. And this is the opposite side. And so remember that the sine of theta is the opposite over the hypotenuse. So the sine of theta is the opposite side length over the hypotenuse. And what's the length of the hypotenuse, by the way? Since it's going from 0, 0 to a point on this circle, right? This circle is what? Radius 1 always as I go along. So this is 1. This is a unit length. So sine of theta is whatever this height is divided by 1. Well, anything divided by 1 is itself. So this height is actually, this height here to here is actually sine of theta. Similarly, cosine of theta is adjacent over hypotenuse, so cosine of theta will be this length, right, over 1, and so this length is cosine of theta. Okay. Not going to need that for this triangle, though. I just need the height, which is indeed equal to sine of theta. So this is just 1/2 sine theta is the area of this triangle OAP. Okay. Next, I want to look at the area of sector OAP. What do I mean by sector? I mean the pi piece. So now OAP, I'm going to go OA, and along the curve here, the circle to P, this pi piece, right? It's a nice little pi piece. Cut you a slice of pie. That wedge right there, what's the area of such a circular sector? It's 1/2 the radius squared times the central angle theta. Of course, that has to be in radians, right? So that's important. And so what is the radius of our, what's the radius? Well, here's a radius, or here's the radius, right, which is what? 1, right? The radius is 1, and the central angle is just theta. So this is just 1/2, 1 is r squared theta, right, using this formula. So it's just 1/2 times 1 is 1, and 1/2 theta. It's the area of that sector. The last thing I need to look at is the area of a bigger triangle, triangle OAT, triangle OAT, okay? OAT, see that big one there? What's the area of this big triangle? Well, it's got the same base, 1/2 base times height, but what's its height? What's its height? Well, now I'm going to make use of the fact that the tangent of angle theta is opposite over adjacent for a right triangle. Notice this big triangle, unlike triangle OAP, which was not a right triangle, triangle OAT is a right triangle because this is 90 degrees. There's the hypotenuse, right? But the tangent of theta for this big triangle is the opposite side length, which is what we're looking for, over the adjacent side length. And what's the length of the adjacent side length? It's 1. So tangent theta is opposite over 1. Tangent theta is the opposite. So this indeed length is equal to tangent of theta. And so the height of our triangle is tangent of theta. So it's 1/2, the base was 1, the height was tangent of theta. We get 1/2 tangent theta. Okay. Now, what do we have now? Clearly, the area of triangle OAP is less than the area of the circular sector OAP, right? Because the circular sector OAP has this little crescent section here in addition, right? So that area is going to be more. And certainly, the big triangle has the biggest area of all. So I can make this inequality. The area of this smaller triangle, 1/2 sine theta, is less than or equal to the area of the circular sector, is less than or equal to the area of our big triangle. And now I have an inequality, okay? So what I'm trying to do, remember, is, if you remember, to prove this limit right here, okay? So I'm trying to get sine, well in this case sine theta over theta is what I want to get in the middle. I want to get sine theta over theta in the middle, bounded by two functions, and then see if I can apply the squeeze theorem. In order to do that, I'm going to divide by 1/2 sine of theta. And we can do that provided, you know, we keep theta from going all the way to pi over 2. So we're talking about basically between negative pi over 2 and pi over 2, I could draw this construction. But in that case, if I want to, in this case, let's just keep it from 0 to pi over 2, so sine of theta is positive. I get a similar argument if sine is negative, it just changes the direction of the inequalities. But let's suppose theta is between 0 and pi over 2. Then this is always a positive quantity and the inequalities don't change. Well, 1/2 sine theta divided by 1/2 sine theta is 1. What is 1/2 theta divided by 1/2 sine theta? Well, the 1/2s cancel. I'm just left with theta divided by sine theta. Okay. Now, 1/2 tangent theta divided by 1/2 sine theta is tangent theta divided by sine theta. Now, I just want you to simplify that, though. What is tangent theta divided by sine theta? That is sine theta over cosine theta divided by sine theta, which is sine theta over cosine theta times the reciprocal 1 over sine theta. Right. Sine thetas cancel. I get 1 over cosine theta. I'm going to put that there. So 1/2 tangent theta divided by 1/2 sine theta is going to be 1 divided by cosine theta. Okay. Now these are all positive quantities if theta is between 0 and pi over 2, and therefore, what if I have 1 is less than theta over sine theta is less than or equal to 1 over cosine theta. If I look at the reciprocals of all these, they will have the reverse order of inequality. In other words, the reciprocal of 1 is 1. The reciprocal of theta over sine theta is sine theta over theta, which is what I'm trying to get to. And the reciprocal of 1 over cosine theta is cosine theta. Now the inequalities are just changed when I do that. Okay? But here's the bottom line. It doesn't matter the direction of the inequality, right? They're both the same direction, and so sine of theta is squeezed between 1 and cosine of theta for all values of theta greater than 0. I can do a similar argument and say the same thing essentially for values less than 0, but close, right? But less, less than 0, but close to 0. So between negative pi over 2 and pi over 2. And clearly, the limit as theta goes to 0 of 1 is just 1. It's a constant function. All right? And here, the limit as theta goes to 0 of cosine of theta is continuous at 0. Cosine of 0 is 1. Both limits of our bounding functions are 1 as theta goes to 0. And so by the squeeze theorem, we now have proven that theorem, or that limit, excuse me, the limit as theta goes to 0 of sine theta over theta is 1. All right, so we've proven that theorem. Of course, up here, I've just replaced theta with x. It doesn't matter our variable that we use. So sine of whatever going to 0 is of the sine of whatever over whatever is going to be 1. So this is an important limit. Okay, so we've proven that limit in quite a long and exaggerated way, but important nonetheless. So again, don't get bogged down in the details. There's a lot of geometry, but it's kind of neat, and I like to see this proof. Involves the squeeze theorem again, and it is a common way of finding certain limits using these geometric relationships. What I'm going to do now, though, is say that from now on you can assume this limit is true. And you can use that. You don't need to prove it like I just did every time. But I'm going to use this limit now to prove this one. I'm going to use this limit to prove this one. And now that we have that in our bank, so to speak, to pull from, I'm going to find this one. And I'm going to recall, first of all, the Pythagorean identity. Right, cosine squared plus sine squared theta equals 1. Well, notice if I solve for sine squared theta, I get 1 minus cosine squared theta. This is the difference of squares, by the way. It's 1 squared minus cosine theta squared, and so I can factor it as the difference of squares. And this is important because what I'm going to do is I'm going to start with this limit, and I'm going to prove it is indeed 0. Now I can't just plug in because cosine of 0 is 1. 1 minus 1 is 0. I get 0 over 0, right? So this is indeterminate form. I can't plug in directly. But what I'm going to do is I'm going to transform this trig expression into something else, and I'm going to do it using this relationship here. And the first thing to note is I've got 1 minus cosine x. Well, that's like 1 minus cosine theta here. If I multiply 1 minus cosine x by 1 plus cosine x, I know then I get 1 minus cosine squared x, which is sine squared x. And getting sine in the picture with an x down here, I think is going to be good because I know something about this limit. So I'm trying to get this limit into the picture. So I'm going to multiply top and bottom by 1 plus cosine x. And this may give you, this may look familiar to you. You probably, I hope, in trigonometry remember verifying trigonometric identities, where you start with one expression and show that it's equal to the other by a sequence of simplifications or trig identities, right? Factoring and other techniques. So that's basically what I'm doing here. And so that skill that you learned in trigonometry is important for us, right? So now what do I have? When I multiply the top, I get, as we said, 1 minus cosine squared x, right? FOIL that out. The inner and outer are cosine x and negative cosine x. So those cancel out. And on the bottom, I have x times 1 plus cosine x. And I'm going to leave that factored. I'm not going to distribute the x through. Now up top, we said that that is equal to sine squared x. Okay. And now comes the part where I need to pull out this thing. Okay, so how do I do that? Well, what I'm going to do is I'm going to break this fraction up into the product of two fractions. Okay, and the first fraction I want is sine x divided by x. Right, because I know what's happening to that as x goes to 0. What's left? Well, I've got sine squared x. That's sine x times sine x. So I have another sine x left up top. What's left on the bottom? I pulled out this x, so what's left? 1 plus cosine of x. Okay, so this is, I haven't done anything. This is the same as this expression, but I haven't broken it up. Now, basic limit laws. The limit of a product is indeed the product of the limits, provided what? What has to be true for me to do what I'm doing right here? Well, remember from the limit laws, these two limits must exist. In order to do this, these two limits must exist. Right? Does this limit exist? Yes, we just proved it with the squeeze theorem, right? The limit as x approaches 0, sine x over x is 1. Right? So it's real important to separate that. You need the limit here. You can't, by the way, sine x divided by x by itself is never equal to 1 for any value of x. Okay? It is never equal to 1. But the limit as x approaches 0 of sine x over x is 1. So you need to understand the difference there. You cannot just simply say sine x over x is 1. You need the limit in front of it. Now what about this? Well, this function is continuous at 0 because when I plug in directly, I get a real number. Sine of 0 is 0. Cosine of 0 is 1. I get 0 divided by 2, which is 0. 0 is a real number. 1 times 0 is what? 0. And there is the proof of our second limit, right? The limit as x approaches 0 of 1 minus cosine x divided by x is indeed 0. So these two trig limits we can use. Okay? And so let's take a look at some other examples then real quick here. Let's find the limit as x approaches 0 of tangent x over 5x. The idea again is to make use of these two limits if we need to. I would plug in directly like we were doing at the beginning of the last video and see if we get something, but what do I get? Tangent of 0 is 0. 5 times 0, 0. This is, again, 0 over 0 form. I can't just plug in directly. But when I see tangent x, I don't see a tangent here or here. Does anyone have any ideas about what I could do with that expression? Well, I hope some of you are saying, hey, I know something about tangent x, and that is that tangent x is sine of x divided by cosine of x. That's the same thing as tangent x. And now I can do a little rewriting here. When I'm dividing a fraction by 5x, that's the same as multiplying that fraction up top. Multiplying by what? The reciprocal of 5x is 1 over 5x. Okay? And now what I'm going to basically do is just rewrite this in, because now I see what I want. And that is, I see that sine of x over x. And since I'm taking the limit as x approaches 0, I'm going to know what that limit is. And so all I do is a little do-si-do here. I'm going to swap the cosine x with this x here. And I can do that because all I'm doing is multiplying these things in the denominator together. And cosine x times 5x is 5 times cosine x times x is x times 5 times cosine x, any order. So I'm going to take the x over here and put the cosine x over here with the 5. All right? So these are the same expressions. It doesn't matter the order I multiply in down here. But now, again, like above, I have a limit of a product. This is equal to the product of the limits, provided what? Provided these two limits exist. Okay. So you should break it up this way by the basic limit law, right? Basic limit law. Provided these two limits exist. Does this limit exist? Yes, that's the one we proved. It's 1. Does this limit exist? Yeah, it's continuous at this function at 0. I can plug in x equals 0. Cosine of 0 is 1. And I get 1/5 here. So I get 1 times 1/5 is indeed 1/5. And that's the limit of tangent x over 5x as x goes to 0. Let's look at a few more real quick. Here's one that when I first look at it looks like, hey, isn't it just, aren't we done with it? Isn't it the same as what we have here? But it's not quite. Of course, I've got a different variable than x. I've got t. But it's as limit as t goes to 0, sine of 4t over t. Okay? And you say, well, oh, that's easy. We can just take this 4 and factor it out, right? Just factor that 4 out as a constant multiple, and I get sine t over t. Not so fast, my friend. This is not sine times 4 of t. This is sine of 4t. This 4 cannot be factored out. 4 times sine of t is not equal to sine of 4t. Right? Very important that you understand the difference, right? These are not equal. Right? This one has an amplitude of 4, whereas this one has an amplitude of 1. This one has a period of 2 pi, where this one has a period of 2 pi divided by 4, or pi over 2. So different functions, you know, completely. Can't do that. See this limit, I'm looking for the limit as something goes to 0, sine of something over something. That limit is 1. The box contents have to all be the same. X, 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 right? Or theta, theta, theta. Okay? What do I want them to be here? Well, since I cannot factor the 4 out of the 4t, I'm stuck with the 4t. I'm stuck with the 4t in this box. So I want the 4t to be where? Down here and over here. I have to put a 4t in each of those locations. How in the world do I do that? Well, the one down here is pretty easy. When I look at the limit as t approaches 0, sine of 4t, I'm going to put that in parentheses, over t. Again, when you plug in directly, you get 0 over 0, so that's not going to help us any. And so we're going to go ahead and multiply the denominator by 4, so I get that 4t that I need. Of course, I have to multiply the numerator by 4 as well, because I can only multiply by 1. Now, this 4 is going to go down here. This 4 I'm just going to pull out in front because it's a constant multiple. So I'm going to pull that top 4 out. It's a constant multiple, provided this limit exists that I'm going to find. and the other 4 I'm going to bring down here. So 4/4 is still there, right? Just kind of pulled that one multiple out. Now, provided this limit exists, I'm good. The only thing left is to make that t into a 4t. Now, how in the world do I do that? Well, what I'm going to do is just a little slight variable change. I'm going to let y be equal to 4t. Okay? And I want you to note that as t goes to 0, as it is in this limit, then y also goes to 0. Right? Y is equal to 4t. If I were to graph y equal 4t, what would it look like? Y equal 4t, right? As we go to 0, as t goes to 0, right? This is the t-axis, this is the y-axis. Then we're going right to 0. Okay, both the functions t and 4t go to 0. So in other words, as t goes to 0, y goes to 0. So this limit here becomes the limit 4 times the limit as what? T goes to 0, but if t goes to 0, y goes to 0. And what do we have? Sine of 4t, what's 4t equal to? Y. And what's 4t equal to? Y. So I've just renamed 4t y, so I've got y, y, y in all the boxes. And therefore, what do I know about this expression now? Now we're set. Everything's the same. Y, y, y. This limit is 1. 4 times 1 is 4 is the limit. Now, somebody might say, well, hey, if I just factored this 4 out, which you cannot do, is what I'm left with is the limit, is this limit basically, right, with t instead of x, and I get 1. 4 times 1 is 4. If you did your support that way, that is incorrect. Okay, so incorrect support, you can't do that. And so you have to be careful. Now, this is a little perplexing. People get confused when you change variables. It's a common thing that we do in mathematics, though. We change variables all the time, and you need to get used to that. Calculus 2, you're going to do it a whole bunch. But I'll just say, in general, I used 4t here, but if 4 was any other number, I'm calling it a in general, we'll notice that the limit as t goes to 0 of sine of at over t is also going to be always equal to a. Okay? You can imagine if instead it was a 5 here, you can see what's going to happen. And so just think about that, look through that a little bit. That's a little tricky. A couple more we'll close out with, and then we'll be done with trig limits for now. You work on some on your own. This one, if I plug in theta is 0, cosine of 0 is 1, and this would be 1 squared. Therefore, that difference is 0, and 0 on the bottom. So this is indeterminate. We'll do some work. So anyone have any suggestions about what we can do to this expression? In particular, look at the numerator. What can we do up top? If you said factor out a cosine theta, give yourself a pat on the back. That is good. I'm going to factor out that cosine theta. And now I look and say, hey, I see not my sine x over x limit, but I see this limit here, right? This one right here. Limit as x approaches 0, 1 minus cosine x over x is 0. And so I'm going to basically just break this up, right? This is the limit as theta goes to 0 of cosine theta times 1 minus cosine theta over theta. I just kind of pulled the cosine theta out in front of that. The limit of a product, again, is the product of the limits provided what? Provided these limits exist. This one exists, we know. It's 0. That's the one we proved before. Does this one exist? Yeah, I can plug in directly. Cosine of 0, it's continuous at 0, and I get 1. 1 times 0 is indeed 0, and there's the limit. Okay. Last, so again, factoring technique. We've used factoring techniques before, but this time it's a little different because we're trying to get one of those two basic limits to appear, one of these two guys to appear. Okay, and that's the same thing we're going to do in this case here, this last case we're going to do today, or in this video. And Again, if I plug in 0, obviously in the denominator I get 0. Sine of 0 is 0, so this is 0, and this is 0. So again, indeterminate. Got to do some work. Well, what are we going to do up top this time? Again, if you say factor, you're good. I'm going to factor out what? A sine of x. What's that leave me? 5 cosine squared x plus 2. Okay. And now what? Do you see one of our two limits? Sine x up top, x in the bottom. I just need to split that up, right? And I'm going to go ahead and write it as a product of limits. In other words, this I can write as a product, then that's going to be the product of the limits. And so what I'm going to have is the limit as x approaches 0, I'm going to pull the sine x over x together, and then times the limit as x approaches 0. What's left over? Of course, all this up top, 5 cosine squared x plus 2 is left. What's left in the bottom? I pulled the x out from 13x, that leaves me a 13. Right? So we could do it this way. Now this limit we know is 1, and this one is continuous, right? If I plug in 0 for cosine, cosine squared x again is cosine of 0 squared, and cosine of 0, right, is 1. So 5 times 1 plus 2 is 7. So this is 7/13. And so my limit is 1 times 7/13, which of course is just 7/13. That is my limit for this situation, or for this function. Okay, keep in mind too, on finding these limits, we can make mistakes in here. Can you have any way of checking your work? Yeah. Don't forget you can check numerically. You can go back to this function, plug in values of x closer and closer to 0, like 0.1, 0.01, 0.001, and so on, and see what this is approaching. It should be approaching 7/13. Okay. Keep in mind, though, when you are doing any limits involving the trig functions, that you are in radian mode in your calculator. Okay, make sure you're in radian mode if you're using the numerical techniques to estimate limits. Okay, we are going to stop here. In the next lecture. We're going to look at limits at infinity and horizontal asymptotes.